Okay, time for another step question. This one is from the 2004 papers, paper 2. It's the 9th question, which as usual is a mechanics topic question. The question's in front of you on the screen. Please do read it and try to do the question if you wish before watching my answer. Right, I'll start talking about my answer now. What can I say about this one? Well, obviously mechanics questions are testing different sets of skills in Pure, and this one is quite a good example of how you need to work with, let's say, mathematical modeling. Mostly in mechanics, mathematical modeling means drawing diagrams. That's the most important part. I mean, you can do this stuff in your head without a diagram on paper, but it's extremely difficult. And more importantly, don't forget that you're trying to write an answer which will be acceptable to an examiner, and that means that your reasoning and your logic must be visible to them. But in practice, it's I said you can do it in your head. That's in theory. In practice, nobody can really do problems like this without drawing out diagrams. It would be sort of some kind of masochism to try. So I'm really going to focus in what I do over the next number of minutes on showing you how to construct the diagram carefully. Now I don't guarantee I'll do this brilliantly well, but I suppose if I do make mistakes or have trouble with it, then you'll understand the kind of problems that you yourself might face. Alright, enough preamble. The topic is, or rather the substance of the question. We've got a big wall of text here, very common in mechanics questions. They don't give the diagram for the reasons I've just been discussing. Yeah, one of the main differences between STEP and most A-level boards is most A-level boards will give you lots of diagrammatic help. They'll give you a diagram, and all you really have to do is annotate it. Here you have to construct the diagram from the description. So we have a non-uniform solid hemisphere. So what does non-uniform mean? It means that the mass is not distributed evenly. It has mass m and it has radius r. The distance of the center of gravity g of the hemisphere from the base is p, and from the center of the base is root p squared plus q squared. Okay, immediately you should recognize root p squared plus q squared is a hypotenuse length. So it means that we've got a right-angled triangle of sides P and Q. Now the hemisphere rests in equilibrium with its curved surface on a horizontal plane. Then we have a full stop and a new sentence, and you might find this a little confusing. It says a particle mass m, where m is small, is attached to A, fair enough, where A is the lowest point of the circumference of the base. So it's on the circumference of the base, on the edge of the base. And in this new position of equilibrium, find the angle alpha that the base makes with the horizontal. Right. So you might find that break between the two paragraphs a bit strange. First of all, it says it rests in equilibrium. Then it says a particle is attached, and in the new position of equilibrium find the angle alpha. So we might want to take a moment and pause. Even though the first paragraph doesn't have a question, we might want to pause and try to understand what it's saying. Let me now switch to a sheet to write on here. Let's consider what does the situation look like without, in other words, before we read the second paragraph on the first paragraph, without the particle attached. What does that initial equilibrium look like? So to do this, I'm going to have to try and draw, and it won't be that easy. I'll first draw a big circle. I'm not even sure if that's big enough, to be honest. Actions, I'll change that to a circle. So what I need to try and draw is a hemisphere. Obviously I'm going to draw it side on. I'm going to remove half of this. Not easy to judge what is half, is it? Let's try and do this. Maybe, where do I want to do this? So it's going to be in equilibrium, but not with its base horizontal, with its base at an angle. What's about half? That's about half, isn't it? Maybe it's a little more than half. Okay, this will be far from perfect, but let's make that a little further there. Okay, a little further. Alright, now I'm going to try to draw a line. Let me see if I can do this. That's actually not too bad, is it? Maybe I can improve that and then move it so that it, oops, no, I'll need to somehow, oops, move it so that, can I just grab that? Maybe. Okay, this is me just experimenting a little bit. You'll have to forgive my, oops, that doesn't seem to, maybe if I do that it's better. Yeah, maybe actually. Yeah, I like that. Okay. So, apologies for the fiddling, but you know, it does take time to draw good diagrams, and they don't need to be perfect, but they need to be visible. Now, so the idea here is obviously that the ground is, let's say, just here. I won't be able to do this properly, but the ground is here. And actually I won't bother to draw the ground. You get the idea that the hemisphere is resting on a point off to one side because its center of gravity is not symmetrical. It's to one side of the center of the base. Let's mark on the center of the base right now. The center of the base, let's say, is here. Okay. And so, you know, we have a radius here and another radius on the other side. And the point where the hemisphere is touching the ground, the curved surface is touching the horizontal ground, is, let's say, here. Oops. Here. And of course, very important is that point, that second point I've just marked, is directly vertically below the first point I marked. Let's call the first point I marked O as the center of the, we have to consider O as being the center of the circular base. Okay, we're looking at it side on, but that is a circle, of course. Excuse me. Now, I hope it's obvious why this point which touches the ground, let's call this, do we need to give it a name? Let's call this C. Not quite sure why it's called C. C is directly vertically below A. I'll even write this down, although it's not necessary. C vertically A because OC is a radius. OC is a radius, so the vertical line, so that's vertical. Now, where is the center of gravity? Well, if this is an equilibrium situation and there are no particles attached to the hemisphere, then clearly the center of gravity must be on the line OC, mustn't it? Why is that true? Can you tell me why it is that the center of gravity, we call it G, must be on that line OC? Well, obviously the reason is because if it were to one or other side of OC, then that would create a net moment, a net turning effect. The weight, maybe I'll draw the weight like this. Oops, that's not very good, is it? The weight, capital Mg, because the hemisphere's mass is capital M, the weight mg acts directly downwards from the point G, which is the center of mass, and that would create a turning effect if it were to one or other side of OC. Okay, so we're on the way. Well, we're on the way to just understanding the question. We're not yet actually solving any of the parts we're asked to solve. I'll just move that to one side. I'll mark this point as G here, and the force acting downwards is just understood for now. Now, we were given information about this point G. Actually, I've changed my mind. That G will appear on the other side. We were given information about the point G. We were told that two things. First, that the distance of the center of mass to the base is P. Now, what is the distance of the center of mass to the base? Well, if you have a a line or a plane, and then you have a point, if we say the distance of the point X from the line L, what we actually mean, of course, is the shortest distance, or the perpendicular distance from the point X to the line L, or indeed the line L could be a plane. It's the same thing. It's the distance measured, as it were, perpendicularly, which means the shortest possible distance, because obviously, in theory, we could get from X to L in any number of ways. So hopefully that's obvious to you. You've seen questions before in vectors and mechanics and other things where that was discussed. I mean, in my opinion, it's always clearer if the question says the perpendicular distance. Here it doesn't say that. It simply says the distance from the center of gravity to the base. So that means actually this distance here, if this is a right angle. So that distance is called P, and that's a right angle, sorry. There we go. And the other distance they gave us was the distance OG, because they told us that the distance from G to the center of the base, so O is the center of the base, was root P squared plus Q squared. So that means we have a simple triangle here, a right angle triangle with P, root P squared plus Q squared, and Q, as I mentioned earlier. Okay, fair enough. That is the situation in the initial equilibrium. Now we don't really need to do anything with this, and indeed, if you're quite quick on picking things up, you may not have needed to think about that at all before you moved on to the first actual question, but I think most students would find it useful to just mull that over. Okay, what I'm going to do now is remove all of that, or no, perhaps not, perhaps I'll just move to a second page, and now I'll try to answer the question of what is the angle of the base from the horizontal. So notice here the angle of the base from the horizontal, we would mark that, let's say here, we might call that one theta. What we're going to do is attach a particle at one extreme point of the base here, and obviously that will then pull the system downwards on the left, and it will change the angle theta, and the new angle will be called alpha, and we will have to find a formula for alpha using M and P and Q and so on. Okay, so I was just wondering, I suppose you would almost certainly find it useful to think about the question, what is the value of theta in terms of P and Q on this diagram? So I've helped you out a little bit with that vertical line, haven't I? Because this angle here is 90 minus theta, and then we can see that this angle here is also 90 minus theta. So this angle here is theta. So we can see by looking at the sides that the tangent of theta is Q over P in this diagram anyway. So that's really just an observation. It wasn't actually asked for by the question. Actually, before we go on, let me just ask you a little question, because it seems to me I glossed over a point that might be very important and might not be obvious. Let me ask this question. Why is O, well, I wrote an answer here, but it's not really clear, is it? OC is a radius, that's true, isn't it? C is a point on the circumference of this circle, not the base, but this circle, which is a slice through the sphere in the middle. And O is the center of that circle. So why must that line be vertical? Well, the answer is because tangent at C. What is the tangent at C? Well, the tangent at C is the horizontal ground. So the tangent at C is horizontal. So that means the radius at C must be perpendicular to that tangent, because radii are always perpendicular to tangents. So the radius is vertical. So OC is vertical. If you didn't get that clear, then you would have a lot of trouble figuring out the geometry. Yeah. But once that's clear, then, well, certainly this triangle is clear. The next diagram we're going to draw is going to be significantly, well, a bit more complicated. So let's now try and answer the first part of the question itself, which says, find the angle alpha if a particle mass m, where m is small. I'm not sure if that's actually important. Well, yes it is, yeah. So find the angle alpha that the base makes with the horizontal when a particle of mass m is attached to A, the lowest point of the circumference of the base. So on the original diagram, A would be this point here. Okay, so let's draw the diagram again, and it will have to be as big as possible so we can really clearly see the details. So I will, how shall I do this? I think I'll just draw another big circle, as big as I can, and hopefully that will be recognized. Yeah. Now, does that look a bit ellipsy? I think it does, doesn't it? Does that look more, oops, does that look more circular, or perhaps even, yeah, that looks more circular to me. Alright, now, because I've attached a particle to A, I want it to be dipping downwards as much as possible. So I'll start erasing the circle from, I don't know, maybe here. It's probably okay. And I'll just keep going until it looks like a half circle. Does that look like a half circle? No, that's too high, isn't it? Maybe that. Obviously, you'll find this a little bit easier with pen and paper, or rather pencil and paper. But you'll definitely need a ruler to do a good job, I think. Okay, so vaguely that looks something like a half circle. So I'll draw a line as best I can. Okay. And just shift it across. Maybe we can get some, oops, excuse me. It's not really the right angle, is it? If I pull it over that way, maybe it's a better idea. Yeah, that seems to work pretty well. Okay, so let's just erase the edges. Okay, now we have our extremely pulled over hemisphere. Now, let's, I'll need to just create a bit more room so we can see what we're doing. Now let's put the particle first of all. That will be straightforward. At position A, at point A here, we have a particle of mass little m g. Okay. Now, before we continue drawing, let's make sure we understand the physics here. The idea is, because we've added that force, and it's to the left-hand side of the vertical line. Okay, we'll still call it C, OC. So C is somewhere like here or something, and O is somewhere like, that doesn't quite look right, but it's good enough. C and O. O being the center of the base. So that's supposed to be a vertical line. It's not particularly vertical, but I'll draw it. Okay, C is here. So because that mg force, that little mg force, is pulling, let's say, anti-clockwise, we need a clockwise force. So that means that the only other force, which is the weight of the hemisphere itself, acting through the point G, must be on the right-hand side. Okay. Now there won't be much room for this on this diagram. I guess it will be somewhere like here. Yeah. So I'll draw it somewhere like here. And this will be the point G again, and we'll add the force capital Mg, which creates a clockwise turning effect about C. Obviously capital M is bigger than little m, so that makes sense. Now, how are we going to find the angle alpha? What's the angle alpha? It's the angle that the base makes. So the base here is represented by the straight line. The angle that the base makes with the horizontal direction. So that would be alpha there. So we're going to have to find a formula for alpha. How will we do this? Well, in order to see what alpha should be, in other words, to see how much the hemisphere should have tilted over, we need to measure the moments clockwise and counterclockwise. And to do that, since we already know the forces, the main thing we need is the perpendicular distance of the forces from the vertical line, from the pivot. That's right. So the perpendicular distance from the pivot, I'll mark in red here for the left-hand side force, and also red for the right-hand side force. So we need those two distances, multiply them by little mg and big mg respectively, set them equal, and we hopefully will get a formula that allows us to find alpha, to rearrange and find alpha. Okay, not so bad. Of course, to find those distances, well, how can we find them? Let's look at the one on the left here first. Can we find that distance easily? Yeah, actually we can find that distance immediately, because the distance from A to O is just the radius of the hemisphere, of the sphere or circle, and that's r, the radius. And this angle here is trivially, you can see, the same as the angle alpha. So we can see therefore that the anti-clockwise moment is just little mg, the force, multiplied by r, multiplied by the cosine of alpha. So that's easy. The other one's a bit more tricky, but not disastrously so, if we remember what we know about the position of the centre of mass. We know that it has a perpendicular distance to the base of P and a distance to the centre of the base of root P squared plus Q squared. I think I'll use a different colour for this, and inevitably this has ended up being quite small despite my best efforts. I'll draw the triangle like this. I think it should be quite clear. So what I'm drawing here is the same triangle as we drew here, except I flipped it over. Here I put the P part on that side. Now I'm going to put it on the other side, but it's the same geometrical construction. P is here and Q is here. So looking carefully at that triangle, we can see that this point is G. Let me just mark that with an arrow now so it's clear. That's G. So the distance from G to the line OC, which I've marked in red as that little red dotted line, can be found by using the line OG as a hypotenuse. So I think what I'll do for absolute clarity is mark another point here. Let's call that point B, and then we'll magnify the triangle OBG. So there's B, there's O, and there's G. Now you don't have to do this kind of extra illustrative detail in your answers necessarily, but certainly you have to do something like what I've done on the left here. You can't get away with doing this question without drawing that kind of thing out. And the more you annotate it, the better. Yeah, the more you add the names of points, the lengths, forces and so on, the better the diagram will be. And that's why the bigger the diagram is, the better, because if it's not big enough you won't be able to annotate it. I'm already having that problem here, which is why I've had to add this extra diagram for clarity. Now what we have is this distance OG is known to be root P squared plus Q squared. That's the hypotenuse of the triangle that we already mentioned. We don't know the distance OB, and what we want to know is the distance BG, because that is the perpendicular distance of the weight of the hemisphere from the pivot point at C. Okay, so how do we find BG? Well, we need to know the angle. Let's call, which one am I going to use? Yeah, let's call this angle here, what should I call it? Theta alpha. Let's call it gamma. So what's the value of the angle gamma? Because if we know gamma, we can do the sine of gamma as being BG over root P squared plus Q squared. Well, gamma can be found because if we extend this vertical Do you see how we can find that angle gamma? It's not too difficult. This angle here, if we do a bit of angle chasing, this angle here is 90 minus alpha, which means that this angle here is also 90 minus alpha, and that means that this angle, because here we have a right angle, the blue line here is perpendicular to the base, so that's a 90-degree angle, and so this angle here, I won't actually draw it, but the one from the vertical OB to the line of length P, that angle there is in fact alpha. Now just to tidy up my diagram, I'm going to remove those annotations. Right, so we deduced that this angle here is alpha. Well, that's not exactly the angle we want, is it? The angle we want is the angle shown as gamma here. So I hope you can therefore see that gamma is alpha minus the angle within this blue triangle. And the angle within this blue triangle, we can remember we referred to it earlier. Well, I guess we don't need to refer to it because we've got the sides P and Q. So perhaps I'll just ignore what we did before and just write it in that way. So this angle here within the blue triangle, because it has sides P and Q, is arctan, or inverse tangent, Q over P. Q over P. There we go. Okay, that means what's the length of BG? BG, which is what we need, is root P squared plus Q squared times the sine of gamma, and the sine of gamma is the sine of alpha minus arctan Q over P. Running out of space here. There we go. Excuse me. So we've got BG, so we can now calculate the clockwise moment. So let's do that. Clockwise moment equals the force capital Mg times Bg, which is root P squared plus Q squared, sine alpha minus arctan Q over P. It looks a bit messy, but it will simplify down, won't it? Because sorry, what am I saying? Yeah, because arctan Q over P has sine and cosine values that we can easily write down. So let's write out the full moments equation. Equilibrium, rotational equilibrium. It's my shorthand for equilibrium. We have the following. On the left-hand side, we have the anticlockwise moment mgr cos alpha, and on the right hand side we have capital Mg root P squared plus Q squared sine alpha minus arctan P over Q, which we've just calculated. Now simplify, get rid of G, put the capital M on the left hand side, and let's leave cos alpha there for a moment, and now we have root P squared plus Q squared times, and let's expand out the sine here, sine alpha cos arctan P over Q. Well, if you think about what that means, you should immediately understand, well, for those that don't think like this, it's important to think like this, okay? If we have P and Q here, the angle we're talking about is this one, because look, arctan P over Q, so obviously this is root P squared plus Q squared, so the cosine of arctan P over Q is when we use Q, like that, and sine alpha, so that's sine alpha cos theta minus cos alpha, so minus cos alpha, and then the sine of that angle is P over root P squared plus Q squared. So those root terms obviously cancel, and what we can also do is divide by cosine alpha, so that the left hand side just becomes little m r over big M, and dividing by cosine alpha gives me a tan alpha times Q minus P. So here finally I have a simple equation for the value of alpha, or at least the value of tan alpha. So let me write that out. Tan alpha is, well, I'll just skip a step. It's capital MP plus little mr over capital M P, Q, sorry, Q. Yeah. Now I want to make a point here. You deduced a certain angle through some calculations. Make sure to check physically that it makes sense. Here's two ways you can check that it makes sense. First, imagine that little m was 0. In other words, imagine that the particle had 0 mass. Well, what would you expect? In that case, we would revert to this case, where the angle we would get would be the angle theta would have this value. Arctan theta would be Q over P. Now, do we have the same or not? We actually have P over Q. That means I made a mistake. Okay, I just had another look, and I can see I did indeed make a silly mistake. I wonder if you spotted it. But this is the kind of thing that can easily go wrong. So I remembered that this form was this, but I put the Q and the P in the wrong place here. So if you look at, let me just highlight it for you. If you just look at this Q over P here, I've changed to P over Q there. So that was simply a transcription error. So all I have to do now is swap P and Q in my equations, so it's correct. So I get Q here and P there. Let's try and speed this up a bit. Oops. That's P and Q. Alright, so Q over P, Q over P, P and Q, so this is P and then Q. And this is Q. So I apologise, this is not the most riveting viewing you've ever seen, but I suppose it's like real life, isn't it? That's a P, and that's a Q. Alright, now I will be able to make the point I was trying to make before. So first point is that when little m is 0, we should revert to the original equilibrium case. We should get the angle here being arctan Q over P, and we see that is indeed true because this disappears, we get Q over P. Also, what happens as m becomes larger? That's important. If little m becomes larger, well, that means the mass of the particle here is getting bigger. Well, that will pull down more on the left, which will mean that the angle alpha will increase. Does that make sense? Yes, because little m gets bigger means tan alpha gets bigger, means alpha gets bigger. So we have at least two bits of evidence to suggest that this formula is right, and you'll notice there that actually that check helped me to correct my error. Of course, there's no magic bullet for this kind of thing. Checks like that can often pick up mistakes, but they will not pick up every mistake. That's a simple fact. Overall, it's definitely worth doing checks like that as much as you can in mechanics questions. You can use the physical situation and what you know about it to help you check the form of your result. Now, what we're going to do in the next part is try to find a similar formula in the case where the particle is removed and attached to the point B at the other end of the diameter through A. So obviously that means obviously that means that the particle is moved from here over to this point here. Now, to save a bit of time, I wonder if I can cheat a bit and you know, to be honest, actually not, because it's different enough that it's rather annoying. So I'll just draw another circle, again as big as I can, although it can be changed, can't it? So I draw a big circle, a little bit more circular. Okay, that's reasonable, I suppose, maybe. And then a little bit more circular, a little bit more circular. Okay, that's reasonable, I suppose, maybe. And then a little bit more circular, 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 a little b So big circle, what are we doing? We're first going to, now this time, because the particle will be on the right hand side, the hemisphere won't be tilted over so much. It might be only slightly tilted, so I'll start from about there and try to cut out about half. That looks about right. Let's get a bit more space. Okay. Now a long line. And oh dear, that's very strange, isn't it? I wonder why it did that. No idea. Yeah. Don't know how to deal with this. Why doesn't that just become a normal line? Can I move it anyway? I wonder. Whoops. Why doesn't that... Oh. This software is not the easiest to use, I have to say. Maybe here? No, that just wants to do that. Okay, never mind. I suspect what I need to do is draw... Yeah, I think I know what I need to do. It probably interprets it as horizontal if it's quite a shallow angle. Yeah. So now this won't work easily, but I'll give it a shot. Maybe I need to move up the page a bit. I apologise for this delay. I know it's probably very boring. Oh no, I can't do it like that. It's like this. That's it, isn't it? Oops. A little bit too much. Okay, that's good enough, I guess. Yeah. Good enough. Not perfect, but good enough. Now we have our hemisphere. So this time it's not so much angled. So this time that the particle is attached at B, so that this weight is now pulling. Oh dear. This weight is now pulling pulling clockwise, isn't it? So that means that the centre of gravity of the hemisphere must be pulling anti-clockwise. So as before, I can still mark my points O and C, maybe here and here, with OC as before being a radius and C touching the ground. But now the point G will be on the left of that line somewhere, so I'll draw it, let's say, here. And as before, I need to mark on perhaps the... what's the best way to do this? Yeah, I need to mark on the triangle which has sides p, q and root p squared plus q squared. So this one is p, the distance from G to the base, and then root p squared plus q squared being this hypotenuse OG. You can see it's going to be a very similar diagram, but there'll just be some subtle but important differences. Now, the radius are as before on both sides there, and as before the I made another mistake. Little mg is the weight of the particle, not big mg. This one is big mg. So as before, the moment due to the particle is easy to calculate because we know the angle beta is the angle formed here with the horizontal. So all we have to do to find the distance of this is the point B, isn't it? The distance OB, which is the radius r, times the cosine of beta will be the perpendicular distance of that force from the pivot point C. So little m g times the radius times the cosine of beta is the clockwise moment about the pivot. mgr cos beta. That, as it was the case in the previous part, that's easy. The other part's a bit more difficult. Again, let me try and use red to indicate the distance we're looking for is this distance here, which means that we need to use the distance OG, which we know again to be root p squared plus q squared, and then we need to multiply that distance by the sine of this angle here, and again I will call this angle gamma, even though it doesn't have to be the same as last time. So how do I find gamma? Well, obviously I'm going to use basically the same method as before, but just do it carefully because it's not necessarily the same, is it? First of all, that's beta, meaning that that angle there, angle chasing, is 90 minus beta, meaning that the angle formed between OC and the base, this angle here, is also 90 minus beta. The angle okay, so I think what I'll do is expand. It's very difficult to say it without drawing it. So let's draw OG, then a vertical, then this perpendicular to the base, and this line here. That's the setup we're looking at, isn't it? Whoops, that should be horizontal. Very difficult to do horizontal. There we go. That's G. That's O. This length is P. This length is Q. This whole angle is 90 minus beta. And this angle, let's use different colours. So I'll use blue. In blue, 90 minus beta. In red, what angle is that? Is that theta? Let's go back and double check. Theta was the angle opposed to P, wasn't it? So that is theta. Sorry, I just had to check that. No, theta actually is here, isn't it? This one, that's opposed to Q, not opposed to P, as I thought. So theta is opposed to Q. So this one I've marked in red here is not theta, it's actually 90 minus theta. Now I know this is all very fiddly. You can be more elegant than I am, but whatever you do, be careful, because it's so easy to go wrong with this kind of working. And you go slightly wrong, you'll end up with totally the wrong answer. So however you do it, just be careful is what I'm saying. So here we are, in blue 90 minus beta, in red 90 minus theta. That means that if I mark in green, clearly with a little bit of arithmetic, you see we're getting 90 minus beta minus 90 minus theta, so that is theta minus beta. And let me remind you what theta is. Theta is, well, I don't need to, it's here, isn't it? It's on that diagram. So we've got the angle theta minus beta for the quantity gamma that I've marked on my main diagram. So now if I write the anti-clockwise moment, I'll use that angle gamma, which is theta minus beta. It's equal to, so clockwise moment was equal to mgr cos beta, is equal to capital M, the weight of the hemisphere, G, times the length of OG, which is again root p squared plus q squared, times the sine of gamma, which is the sine of theta minus beta. So I'll do exactly the same as in the previous part. I'll set the two moments equal and then try and deduce the value of tan beta. So moments are equal. Equilibrium means that the anti-clockwise moment, little mgr cos beta, let's check that. Oops, little mgr cos beta equals the anti-clockwise moment, which is right there, capital Mg square root p squared plus q squared, sine, well, theta minus beta, let's do it in detail, sine theta cos beta minus cos theta sine beta. and we'll follow the same approach as before. Cancel the G, bring the capital M to the other side, little m r over big M, and we'll leave the cos beta there for now. As before, this root p squared plus q squared will cancel for the same reason, but I'll leave it there for a moment. Now, what's sine theta? We remind ourselves, looking at this diagram, sine theta is q over root p squared plus q squared, so it's q over root p squared plus q squared. Cos beta minus p over root p squared plus q squared sine beta. And just as before, I can cancel out the cos beta on the left hand side by I can divide by that, and the root p squared plus q squared cancels as before. M r over capital M equals, let's see what we've got, q cot beta, no sorry, q times 1, isn't it? Q times 1 minus p times tan beta. And rearranging that gives me what? Tan beta, let's see, I've got q minus mr over m divided by p, capital MQ minus little mr over capital M times p. And again, we should take the trouble to check if this answer for beta makes sense physically. First of all, if if little m is 0, so if little m was 0, we would get tan beta equals q over p, which again makes sense because it reverts back to the equilibrium case without a particle. And if little m increases, what happens? Well, if little m increases on this equation, it means that tan beta decreases, which means that beta decreases. So let's look at the diagram. If little m increases, then we're pulling further and further down this way, which means that beta does indeed decrease as required. I mean, it's assumed in all of this that little m is much smaller than big M, so there's no worry about getting negative values or anything like that. Although I suppose it's quite okay if that happens. I mean, the main point about m being small is that we don't have the case where the whole thing topples over. Anyway, that's absolutely fine. At least it passes the checks. So for now, we accept it, and it looks reasonable. Now, the last part of the question is simply asking us to show this equation. Well, we've just worked out tan alpha and tan beta. So finding tan alpha minus beta is a simple matter of using the formula for tan A minus B. So tan alpha minus beta, let's just change to red, tan alpha minus beta, well, that's just tan alpha minus tan beta over 1 plus tan alpha tan beta. And I can probably fit all this on the page right here, because it's not quite as bad as it seems. If I just write a very big ratio here, tan alpha, let's remind ourselves, excuse me, tan alpha was here. I might be cheeky and just copy this actually. So tan alpha was that expression, and tan beta we've just written down, so I'll put it here, minus, mq minus little m r over capital MP, all divided by 1 plus the product of those two things, okay, it looks a bit horrible, but all those denominators are the same, so all we have to do is multiply by the square of them to get rid of all the denominators, because we need to get rid of MP, so m squared p. So times m squared p squared is the plan. That's equal to capital MP, so if we times by m squared p squared on the top, we get an extra factor of MP, and then we get capital MQ plus little mr minus capital MQ plus little mr because of the minus sign, and then in the denominator we get the m squared p squared factor there plus MQ plus mr times MQ minus mr. Okay, and the last steps are trivial. You see that the MQs cancel on the top, giving 2 times mr times MP, and on the bottom we get m squared p squared plus the difference of two squares, so it's m squared p squared plus m squared q squared minus m squared r squared. So actually we get exactly what we were asked to find. 2m mpr divided by m squared, capital M squared p squared plus q squared, and then minus little m squared r squared, which I believe was the formula we were asked to find. Yeah. Okay, so what can we say about this this example? Conceptually, not difficult. I hope you agree. The only mechanics principle involved is the principle of moments. Is the geometry difficult? Well, it depends what you mean by difficult, doesn't it? Right? I mean, it's finding the angles is not very hard, but it certainly is confusing. And just imagine trying to do this question without having a diagram. Imagine how hard that would be. So I can't really tell you if I think this is a hard or an easy question. I think it's easy to go wrong, but if you don't make any silly slip-ups, it's pretty easy to get to the final answer. Perhaps the most useful sort of educational point is that idea that when you go through these rather complicated modelling problems and you arrive at an answer like that, oops, that's supposed to be a ring. When you when you arrive at an answer like that, take the time to check extreme cases. What happens if something is very big? What happens if something is very small? And try to fit that in with your physical intuition. If it doesn't fit, if it doesn't make any sense physically, then you must have made a mistake. So I hope that was a useful exercise. Apologies for how long it took to do the drawing, and speak to you again soon.